We still have 1 minute, but I just want to make sure that I have this open and we don't take too much time from our invited speaker's talk. So my clock shows that it's just the right time to welcome everyone to the 5th workshop on formal mathematics for mathematicians. So I co-chair this workshop with Jasmine Blanchette, and I must say that I have the reasons to believe that this is because of Jasmine's good work that the workshop was popularized in many communities. So this year we are happy to have as many as 13 normal presentations and 2 invited talks, one of which will start in a moment. So just to give you a brief overview to those who didn't attend this workshop before, we had a meeting in Prague in 2019, before that in Hagenberg in Austria, and as well as in Białystok in 2016. And the first FMM workshop was organized in 2015 in Washington, D.C. All of the meetings were organized together with KICOM conferences, but as yesterday Wolfgang reminded us that as for KICOM, there was KICOM 0. I would also like to mention that actually the name and the idea was born earlier, so something like KICOM 0 was organized in New Orleans as a part of the joint AMS meeting. And I'm very glad that people who attended that meeting, like Ferouz, Bill Farmer, and let me have a look. Jeremy Avigad is also at this KICOM, and my colleagues Artur Korniłowicz and Adam Grabowski and myself, we all were there. So we still remember that nice meeting, and unfortunately Andrzej was not well enough to take part of it, but we still hold the memoir picture that was brought to him from that time. All right, so coming to the present, I would like to introduce our first invited speaker, that is Mario Carneiro. And I think I met Mario first when he, as a student, attended a special session on computer-assisted formalization of mathematics that we organized in memoriam of Andrzej in 2014. He graduated from Ohio State University with triple major in mathematics, physics, and computer and information sciences. And then we learned about his interest in Norman Megill's MetaMath system. So he presented his work on FMM meetings, also in Washington, speaking about generalized continuum hypothesis and the axiom of choice. So the topics were rather advanced and highly non-trivial. And later on, we met also and looked as he very impressively formalized almost 40 problems from the Frey-Vidate's list of 100 theorems. So if we add to this his formalizations in Lean, that would be, I think, 40 now. So I'm still impressed by this amount of good formalization work. And today Mario is a Lean expert, so another system that he touched is developing in a very nice speed. So I'm confident about the future of developing of the Lean library if such developers, such active and energetic as Mario are there. So Mario, the floor is yours.
Uh, Thank you very much, Adam. Could you help me with the screen share? I believe you need to turn it off first. Okay, so yeah, thank you for the introduction. I'm going to be talking today about a project that's sort of been in the works for, I guess you could say, starting at the beginning of the year, but really since 2018 when Lean 4 came around, which is the idea of porting Mathlib. So this is joint work with a lot of people. Um, Daniel Salsum, Aurelian Sawa, and Gabriel Ebner have been working on the tooling, and Wojciech and then Kevin Buzzard, David Renshaw, Jeremy Avogad, Denise Aydin, and Xing Taklam have been contributing to the Mathlib 4 repository. And I expect that a bunch of more people are going to enter the project later once the porting starts sort of in earnest. And I should also mention that this is that I have the good fortune to be able to work on this project as part of my internship at Microsoft Research. Um, I think Adam has already covered most of these things. So I'm a current PhD student in logic at Carnegie Mellon University. I was working in MetaMath for a long time, and since 2017, I've been working on Mathlib, and I've used a number of additional theorem provers in the meantime, and I'm the author of the MetaMath Zero proof language. Um, and you can say hi at the Zulip um, if you ever want to. So Mathlib is a library of formalized mathematics and computer science. It's written in the Lean 3 proof assistant, and it's also sort of the de facto standard library, which is to say that um, almost all public work in Lean 3 is in Mathlib, which is sort of an unusual situation for a language to be in. It's based on dependent type theory, more specifically the calculus of inductive constructions, and it makes no, it uses classical logic and the axiom of choice extensively. There's a very active community, and there are links to the GitHub and the Zulip uh, chat. So here is sort of the growth um, of Mathlib itself in terms of number of lines. There was a similar presentation about Mathlib about a year ago, where we reported that Mathlib is growing and it's reached almost 300,000 lines. Well, it's doubled that since in the past year. So one could say it's growing at an alarming rate, really. This is sort of a similar view of commits by month. Um, Mathlib has sort of two main goals. One of them is to sort of build a standard library for Lean as a programming language. So this is to help support verified programming and proving correct algorithms, and then also to support and provide tactics and decision procedures for proof automation. Um, that is, yeah, tactics and tactic development. And then obviously to build a library of formalized mathematics and to support users working on that goal. And these are very complementary goals. So it's not really just two libraries in one. Now, I wrote this slide 3 years ago in a presentation. And I would say that in the meantime, the math goal that I mentioned has received considerably more attention than the CS goal. And I think that there's several reasons for this. One of them, sort of obvious, is the name, right? We call it Mathlib. Um, and I guess I think in some ways this is a little bit unfortunate. Like it's possible that this might actually be driving away contributors who look at this library and say, I can't do my stuff. It's about math. Um, and um, Also, sort of, there's been some effective marketing, I would say, by a lot of people, but Kevin Buzzard in particular, who has managed to do outreach to mathematicians, which has, I think, skewed the composition of Mathlib much farther towards pure mathematicians, which I think has led to some very interesting effects. It means that, you know, Mathlib is daring to go places where no previous communities have been interested to go. And then also just the fact that the Lean 3 interpreter isn't really performant enough to make the development of optimized and verified data structures really worth it. For reasons that I'll get into, I think that Lean 4 will actually push the balance a little bit more towards the CS applications. There's been a number of notable projects that have been done with or around Mathlib. One of them is the schemes project, which is just developing a workable definition of schemes in Lean. And this is work by Kevin Buzzard, Chris Hughes, and Kenny Lau for sort of the first version, and that was rewritten by Ramon Fernandez-Mir and Amelia Livingston. And then the version that ended up in Mathlib was mostly, I believe, due to Scott Morrison. And formalizing perfectoid spaces is a paper about defining what a perfectoid space is, which is this advanced mathematical topic that was involved in the most recent Fields Medal to Peter Schulze. A formal proof of the independence of the continuum hypothesis. This is work by Jesse and Flores on developing model theory and proof theory in Lean. And then most recently is the liquid tensor experiment, which is proving a technical theorem about something called condensed mathematics. And to be perfectly honest, I don't really understand what that is, but it's apparently a very complicated and important theorem by Peter Schulze. And it was formalized in Lean by a whole bunch of people. This is not an exhaustive enumeration at all. And this one in particular has actually been the subject of several news articles. So it's actually kind of cool to be involved in a project that's being discussed in the news. So just a short history of Lean and Mathlib. Lean 1 was developed in 2013, but I don't believe that there's a public release of this. Lean 2 was in 2015. Lean 3 was released in 2017, and Lean 4, there's the 4.0.0 version came out in January of this year. But I would say that it's still sort of in an alpha stage. It's still changing very rapidly. The Lean 2 math library was developed by Jeremy Avigad, Floris Van Doorn, and Rob Lewis, and several other people. And Lean 3 was not backwards compatible with Lean 2. And because there were a bunch of new features and we wanted to write things in order to take advantage of those features, we basically started over from scratch. We used the old library as inspiration, and Mathlib was sort of born around then. And so Mathlib is the latest version of the Lean 3 math library. It's been developed by hundreds of contributors. And Lean 4 is, again, not backwards compatible with Lean 3. And because of mostly because Mathlib is so much bigger, we've decided that we're not going to try to do that again. We're not going to try to start over and just use it as inspiration. We really went to port the library. So just for sort of reference, what happened in the Lean 2 to Lean 3 transition. So Lean 3 added a bunch of features around the metaprogramming framework. Tactics became an actual sort of language rather than just, 2 or 3 things that you could do. The elaborator was scaled back somewhat in order to avoid poor error messages around backtracking and timeouts that would happen when you're trying to solve sort of higher order unification problems. These are an undecidable problem, but you can sort of just try a lot of things, and that's what it did. And it caused some flaky proofs. So Lean 3 scaled back the elaborator, but that means that now proofs that worked in Lean 2, you can't just copy and paste them and they would work. So a reinterpreted Lean 2 file would generally have errors all over the place, and there would be little syntax differences everywhere. So manual porting really required some heavy touch-ups. So that's sort of why Mathlib was loosely based on the Lean 2 library, but it was mostly written by hand from scratch. Now, the Lean 2 library is about 40,000 lines. This was all eventually ported to Mathlib within the first year or so, most of it within, just the first couple months, but the stuff that wasn't so important came later just to make sure that we had everything covered. For comparison, Mathlib is now 600,000 lines of code, and moreover, it was 450,000 lines of code just at the beginning of this year. So it's huge and it's growing quickly. So we really have to think differently about how we're going to approach this porting problem, because if we just try to do it by hand, we might literally be outpaced by the growth of mathematics. So Lean 4 is a complete reimplementation of Lean inside Lean itself by Leonardo de Mora and Sebastian Ulrich. The implementation started in 2018, but the first stable version was released in January of this year. It's way more extensible than Lean 3 is. So third-party libraries like Mathlib can override or extend almost any part of the system. It compiles to C, so that means that tactics aren't being interpreted anymore. They're basically, you compile them, and then you get a binary, and then you run the binaries sort of link into Lean itself for a later file. So this provides a huge boost in speed for user-written tactics. It also provides a much more powerful sort of macro and syntax engine for being able to do sort of first-class DSLs. And as an example of that, the do notation is significantly more powerful than Lean 3, or indeed Haskell, I would say. It's really a domain-specific language for imperative-style programming. So Lean 4, I would say, is inspired by Lean 3. It's not really a upgrade, and there's no attempt at backwards compatibility. So it has most of the basic concepts, but it's really not mimicking it at a syntactic level. So we have theorems and definitions and expressions and tactics and attributes.
Dai că cocot mă la conferințe, dai.
Is someone asking a question? Okay. So the Lean, one nice thing here is that the Lean 4 kernel is actually mostly an extension of the Lean 3 kernel. So it adds several features. So nested and mutual inductives are now in the kernel. They were simulated in Lean 3, and this caused a number of issues. They're natural number and string literals. So now the kernel itself knows about, large numbers. And in particular, functions like nat.add will actually be implemented by the kernel using like GMP big num addition. So this, I think, will be good news for people who want to use Lean as like a CAS or something like that. I think that brute force is really a more reasonable approach in Lean 4 than it was in Lean 3. So Lean 3 has a thing called macros, which have nothing to do with what Lean 4 calls macros. These are handled differently. There's opaque definitions, so you can define a thing and then forget what the definition of that thing was. And there's a kernel primitive for trusting the evaluation of a compiled Lean expression. So this adds to your trust base, and it will show up in the axioms list. But if you want to use it, you can evaluate like a Boolean term and then acquire a proof that it is equal to true if you run the thing and it is equal to true. So there's a bunch of minor syntax changes. So for instance, like instead of begin end blocks, now it's by blocks. And match doesn't need end anymore. You write functions a little bit differently. And there's generally much more reliance on white space sensitivity instead of punctuation. Tactics are now sort of integrated with macros. They're in some ways handled the same way as terms, and in some ways they're handled like macros. Elaboration is sometimes stronger. There's some things that you can do in Lean 4 that you can't do in Lean 3. And there are some features of Lean 3 Elaborator that were dropped for more regularity in Lean 4. Type class inference is different in technical ways. And many Lean 3 tactics just don't exist yet, either because they were omitted on purpose or because maybe we have an incompatible design, or maybe they just haven't been implemented yet. Okay, so with all of that, somehow we have 600,000 lines of code written in this language, and then we want to translate it to this incompatible language. What are we going to do? There's several options that we can use. So one option is one that I'm quite familiar with. This is the idea that you take the logical material at the bottom, and then you translate that material into the new kernel. So you run Lean 3, you get some elaborated expressions, you type check them using the Lean 4 kernel. This actually works, although it is very sensitive to the unfolding heuristics matching. So Lean doesn't tell you how a thing is proven to be definitionally equal. So it has to do those proofs on the fly in the kernel. And if you don't do those proofs in exactly the same way, you might end up on a wild goose chase where the original wasn't. So that can cause huge performance problems. And the worst case scenario for definitional unfolding is, I don't know, somewhere around the end of the universe time as far as how long it would take to check these things. So you really don't want to fall off that cliff. However, we have done this, and I believe you need to run a port of Lean 4 for this to check, but we can actually port all of Mathlib into Lean 4 kernel terms and check that those kernel terms are correct. So the result is a bunch of compiled Olean files that can be imported into Lean 4 files as though they were other Lean 4 files, except the Lean 4 file doesn't exist. It's just this Olean binary that's providing the logical content. Now, there are some drawbacks here. The obvious one is that it doesn't produce source files. Okay, so well, you can imagine doing some sort of hybrid build process here. So that is to say, you have some Lean 3 files and you compile them, and then you get these Oleans, and then you use those Oleans in more Lean 4 files. So you have some Lean 3 files and some Lean 4 files, and they're sort of coexisting, and you've got some sort of hybrid Mathlib. A drawback of this is that the Lean 3 files can't really refer to the Lean 4 files because they don't have access to the environment that, even though they're being translated into Lean 4, where at that point they might refer to Lean 4 things. When they're still in Lean 3, they can't refer to those things, and we're not doing the porting backwards. So the Lean 3 files are really only able to refer to Lean 3 files, which means that you have top-down translation. You start at the leaves, the highest end stuff, and then you translate those to Lean 4, and then you work your way backwards. But there's a bigger issue, which is that a lot of very important extra logical metadata is lost. So that means things like tactics, elaboration hints for definition unfolding. So this is when you unfold a definition, it will make use of certain other definitions in order to tell it how to unfold it without it looking like a mess. Without that information, using the definition becomes a lot harder. Attributes, simplemmas, notations, these are all gone. So while you can import this file, the theorems look terrible and are hard to use. So additionally, Lean 4 has a bunch of definitions for built-ins. Like I mentioned that nat.add gets this GMP boost in the kernel. We really want to use that nat.add. We don't want to use like some sort of mathlib.nat.add that gets ported from the Lean 3 nat. So we want to align the one definition to the other. But if you make an alignment and that alignment isn't definitionally equal to what it would have been, then that can break the translation, because now when anyone tries to unfold it, they're going to see something else, and something's not going to type check anymore. And then to make things worse, some alignments that we actually want to do are not definitionally equal to what they used to be. And in fact, some definitions are just completely different. Like plus had the type alpha to alpha to alpha in Lean 3. It has the type alpha to beta to gamma in Lean 4. It's just the type signature is just different. So you can't just replace one for the other. Okay, so what else can we do? Well, one thing that we could do is we run lean3, we get the Olean files, and then we reconstruct a lean4 syntax that would have sort of the same effect as those Olean files. Now, this is doing a little bit better because rather than just the pure logical content, an Olean file is this binary file that represents essentially the result of compilation of a single lean file. And this is what's used when compiling later lean files. They're going to access these Oleans. So those files contain everything that lean needs in order to understand downstream files, which means it includes notations, attributes, things like that. So we can use that to reconstruct the syntax. So this allows you to get a result which is pretty similar to if you were to use the lean3 print command to see what a definition is, because that represents like how lean understands the term after it's been compiled. And then tactics, well, you use a tactic inside a definition, they generally have some characteristic proofs, so we can maybe reconstruct the tactics that produce those terms. And then maybe in some cases you can't do that, so maybe we'll change the tactics in order to make them more explicit so that we can always tell how you're using the tactics. Well, I mean, I say that, but in practice, it's actually quite hard. I mean, this is essentially inverting a program, right? You're saying, oh, given this output of a program, what program produced it? And that's just not that's not a well-defined mapping. I mean, undecidable isn't even the right word. Um, and it also doesn't capture any file local structuring commands. So things like local notations, variables, sections, and namespaces. You'll sort of get some information about namespaces by looking at the definitions that are being made, but the namespace itself, where it starts and ends and so on, that information is lost. These are all just sort of structuring things. And then if we want to produce lean4 source, we need to somehow reconstruct that. And then local attributes or attributes that remove themselves. Some attributes are just there in order to do something, and then they like erase themselves. And then also there's a bunch of auto-generated definitions. So you're looking at this Olean file and it contains a bunch of definitions. There's a bunch of auto-generated definitions mixed in with those. There's definitional lemmas, there's theorems auto-generated by the inductive command, there's definitions generated by tactics. And we don't want to count those somehow, like those, like, I mean, we want those to exist because we're going to refer to them later, but we want the tactic that produced them to produce them. We don't want to just port them to and end up with these ugly things. And then definitions by pattern matching are already compiled. So there's a thing called the equation compiler that's going to turn a definition by pattern matching into a definition using basic recursors. And then we have to somehow undo that process. And that's pretty hard. Okay. Well, another option would be to look at the lean3 file and then parse it, right? So we'll just write a lean3 parser in lean4 and use it on a lean3 file or a snippet and use it to produce lean4 content. Now, this is a very flexible approach because it means that we can actually, like, we could even have a lean3 snippet inside a lean4 file. You can sort of do gradual lean3, lean4, sort of intermingle them. Maybe just have some kind of lang directive here in order to say that we're working in lean3 now. And then you just call the lean3 parser that's going to do the work. For Mathlib, we'd probably want to target this on a full file that's just written in lean3 and then either translate it into lean4 syntax or just import it and act as though that lean3 file were in fact a lean4 file. And since, as I mentioned earlier, lean4 has a focus on versatile syntax parsing, and also it's being used to implement a language that's very similar to lean3, namely lean4, you would think that this is a good match. Well, it's not that easy, unfortunately. The lean3 grammar is not context free. You can sort of describe it with a BNF, but there are a lot of little lies. There's things like the expression grammar is extensible. They're local notations. That means that while you're in the middle of parsing an expression, the expression grammar changes and then you end the expression and then the expression changes back. So that's not something that you can do with a BNF. And the parser is very stateful. Every command is executed as soon as it's parsed, and this has observable effects. You can define notation, and then the very next line is you using the notation. And the parser is it can use VM code, so the parser can call into, like, you can write the parser inside Lean itself, and then the sort of backend is going to call into VM code that's going to execute this parser in order to parse the remainder of the text. And that parser can do sort of arbitrary stuff. It can use tactics, it can use IO, it can do whatever it wants. The VM code needs an emulation of the Lean 3 environment in order to call tactics and built-ins. And yes, obviously this is Turing complete parsing problem. So I summarize this as saying that in order to parse Lean 3, you have to be Lean 3. Okay, it's not really feasible for an external program to parse Lean 3, which is a little unfortunate. On the other hand, Lean 4 parsers are more restricted. So parsing happens all at once before execution. Parsers can't do I/O. They're not even monadic. They can't change the environment either. So while I think this is a good thing, I think that restraining the parsers to something a little more sane is a good idea. It does mean that this is not a match that fits well. So what if instead we modify Lean 3 in order to produce the result of parsing? So we'll construct an AST on the side while we're doing our thing, and then we'll export that AST into some format. And then we'll load the AST. So we'll write the AST into some interchange format, and then we'll read the AST into Lean 4, and then we'll sort of parse that AST, which of course is much easier, in order to translate it into Lean 4 syntax. So this really ensures that we'll perfectly mimic any Lean 3 weirdnesses, and there are a number of Lean 3 parser weirdnesses, which you can read all about on the Zulip thread that I've been keeping up. Because Lean 3 is doing the parsing. And this also gives us all sorts of syntax that was not available from the earlier approaches that I described. So we'll get like tactics. So we can see the by start, we can see a tactic block, we can see the exact structure of the tactic block. We really know what that program is. We'll get pattern matching definitions, and then we also get all that file local stuff like variables, sections, namespaces, local notations. A drawback of this is that we have to go through Lean 3. We have to find every single place where it parses something, every command, and the grammar is not small. And in order to instrument it, to add these AST nodes, to collect it, and to export that. The good news is that's done. So I'm happy about that. But how are we going to handle changes to elaboration? So even though we know that Lean 3 wrote, some term that says apply this to that, and it doesn't specify some implicit arguments. Maybe Lean 3 could figure out those implicit arguments. Lean 4 is using a slightly different algorithm. It can't figure it out. An example of this is that Lean 3 uses a different elaboration strategy for recursors. It will sort of generalize from the goal, whereas Lean 4 will work sort of forwards for these higher order problems. And the forwards method is actually less likely to succeed in the majority of cases, which means that if you actually use a recursor in Lean 4 directly, if you write nat.rec of something, it's probably going to fail unless you provide the motive. And similarly, how do we handle tactic changes? So, Lean 3 is going to call simp, let's say, and then we know that Lean 3 called simp will put by simp, and well, what if simp does something else, or what if simp just fails? How do we fix the proof? And then of course we actually need implementations for all of the tactics. So the meta framework is not really something that we're planning on porting. We could, in principle, have some kind of layer where we have the old code and so we have some sort of interpretation layer to allow Lean 3 metacode to be written in Lean 4. But because there aren't that many tactics, we think it's more reasonable to just port them by hand and maybe reinvent them in the process. And then some commands are just manipulating some state that doesn't exist or is expressed differently in Lean 4. There's a precedence command that says set the precedence on an individual token. And that's just not a concept that exists in Lean 4. So what do? I guess delete them? But I mean, maybe that'll break something, unclear. And then finally, there's sort of the obvious approach, which is you take inspiration from the old files, you write a new file by hand. This is obviously going to give you the best quality results, and it's able to adapt to areas where Lean 4 is just too different for a porting approach to work. And it's also got a very low startup cost. The only thing that you need is for people to know how to write Lean 4 code, which, I mean, there aren't that many people who do write Lean 4 code right now, but assuming we get to that point, then people can just, look at the old proof and figure out their own way of coming to a new proof in Lean 4. The drawback of this is sort of obvious. The porting process itself is going to take at least a month, I would guess. And in that month, there will be more material, and then we'll have more to port. So we really have to worry about ongoing changes with this approach. Mathlib gets 10 PRs a day. Should we maybe stop the world and then just say, okay, everyone, we're going to port all at once now, organize some kind of massive porting job, and then it's done, and then we're all Lean 4 from then on. Or I mean, that could be done if we we get everyone together to work on it. We have a lot of contributors, but it's also a lot of free hands. Although I would say that the skill set for porting is not really the same as for writing new mathematics. We have a lot of mathematician users, as I mentioned, and I'm not sure that I want to subject them all to the porting experience, because porting, you really need to understand Lean 3, you need to understand Lean 4. To write new mathematics, you have to understand the mathematics and you have to understand formalization. It's really a different skill set. Another option is to sort of do this in pieces. We'll like freeze a file level or something like that and port from the bottom up. One issue with this is that, well, you're going to have lots of race conditions where like he's working on this and then this file got frozen and now we have to make sure that it gets copied over or something. Or maybe we fork Mathlib. We'll have the Lean 3 Mathlib and the Lean 4 Mathlib, and then we'll start moving things to Lean 4 while Lean 3 keeps on evolving. And I mean, this has exactly the same problem. There's, you have to make sure that every theorem that you write in Lean 3 gets transferred over to Lean 4. Okay, so I told you a bunch of approaches to what we can do here. What are we actually doing in practice? Well, I would say that these two approaches, the Olean and the Lean 3 port, are basically strictly worse than the syn port, because you don't need to reconstruct syntax if you've got the syntax. If you know what the actual AST was, then you can just use that. And similarly, you don't need to parse Lean 3 with the syntax port. So we're really approaching this with multiple approaches at once. So there's a repository called Mathlib 4. You can find it on GitHub. That is sort of a from scratch implementation of Mathlib foundations in Lean 4. Here's where we intend to implement most of the tactics. There's a couple foundational theories like data.nat.basic. That's just, the elementary theory of natural numbers. It's super common and very useful and not too hard to port. So this is sort of the thing where it's easier to just port it by hand rather than wait for the full porting architecture to come along. And then also the porting tools themselves are going to make reference to a bunch of syntax. We need that to be available. We're also making use of bin port. So we have a way to translate this Lean 3 proof data into Lean 4 Oleans, and this is useful for getting a context, for being able to jump right into the middle of Mathlib and still be able to type check what's going on. And that gives you sort of more parallelism if you've got a bunch of people working on separate files. This allows you to break the dependency chains between Lean files. And then synport, as I mentioned, is translating the AST data into lean4 source file. So there's a fork of lean3, which implements this --AST command line option, which will just spit out all the AST for every lean file that it sees. And then it can be pulled into, there's a mathport tool that will produce lean4 files, and then you can use it as a starting point for manual editing. So there's a few ways we can improve this. For instance, while we're collecting the AST nodes, we can also attach elaboration data. So lean3 keeps chugging along. It gets some elaborated expression. We can then attach that elaborated expression to the AST node that sourced the expression that we're looking at when there exists one. And this is useful for synport when it's, so we can run the syntax porting with the lean4 elaborator available. We'll generate some syntax, give it to lean4, see whether it likes it, whether the elaborator is okay with that. If it's not, then we can try something a little bit more explicit. So if the syntax is not going to elaborate the way that we want it to, and we know how we want it to elaborate it because we have access to the lean3 expression that we are aiming for, then we can select some more explicit syntax or not. So one thing that is a trade-off here is that if lean4 doesn't accept a certain piece of syntax, then maybe we could write out this full proof term, but for a user, that might actually be less helpful than just sticking sorry there and asking the user, the porting person, to fill in that sorry, instead of giving them a bunch of junk that they're just going to have to delete anyway because they don't want that in the file. Another thing that we could do is to add more actually backwards compatible syntax to lean4 in order to ease manual translations, to make copy paste more of a viable strategy. So if we actually want to get rid of this, though, then we'd have to do some kind of post-processing step in order to remove the syntax. I think this is a little bit more feasible, though, because lean4 has more, lean4 actually does, like, we don't have to instrument lean4 to produce an AST. It is actually producing an AST. So it is actually possible for a lean4 file to sort of be parsed and then regurgitate a pre-printed version of itself. That's not too different from the original. So we can use that in order to do things like linters or code actions, and we could use that in order to remove syntax that we don't want. And then binport is also, it needs some kind of a line annotation or something on these ported files in order to help it stay in sync. As we add more things, we're going to want to do more realignments. Those realignments are going to cause more realignments down the line. Even if the alignments are not definitionally equal, that's okay as long as the downstream uses are also not realigned, realigned. So that is to say, if you change something for something with the same type, then but if it's not definitionally equal to the old thing, then whenever anyone unfolds it, then it's going to break the proof. If you change something for something with a different type, then it's just going to break every single use of that definition. So all of those downstream uses have to be realigned as well. But you can do that if the number of uses are few enough. So here's some examples just to give you a sense of, I haven't shown that much lean3, lean4 code, but you can see here what the kinds of differences that you're likely to see in the general case. For the most part, these are fairly similar. I mean, they were designed to have a similar syntax, but you can see that, you know, the matches used to have ends, they don't have ends anymore. The limiter changed. Instead of for all, we've got this like AGDA style arrow. And then some names of like or is capitalized now. So these are all things that we have to handle in the port. Here's another example, translating a class. So this is part of the algebraic hierarchy. We have a bunch of classes and they have fields. So a lot of the syntax is very similar. There are things like, well, here you used to, use this dot notation in order to say, I want to call this tactic when the user doesn't provide this field. Here, the syntax for it is a little bit different. The for alls are different again, and the where instead of using snake case convention, we're now using camel case or capital camel case. So this is all part of alignment and naming heuristic changes. And this is an example of a proof. So, we used to use begin end. Now we're using by. We used to use these brackets. Now we have this dot notation for being able to do grouping and sub goals and things. Now, this is actually not the, this is using, you'll notice that I have induction prime here. That's because Lean4 has an induction command, and the induction command has a significantly different syntax. It actually has like case something arrows something for each of these cases, which gives it a more tree-like structure. But for a porting tool, it's difficult for it to completely move around those types and figure out like how many of these name like this. Like both of these names are for the second case. Neither of them is for the first case. It's not entirely obvious to a syntax porting tool. So it's easier just to have a more similar tactic. So this is quite possibly the largest source level proof porting project that has ever been done in a theorem prover. And Mathlib's high and growing activity rate and many contributors lead to some interesting logistical challenges. I do think that the techniques discussed here apply generally to any source level translation. In many ways, Lean 3 is sort of the worst case for this kind of thing. Everything that can go wrong has gone wrong in this pair of systems. So I would imagine that if you wanted to translate from Coq or Isabelle to Lean, or even to some other language, as long as it also had the same capabilities as far as metaprogramming is concerned, I think it would follow a similar path. The main thing that saves us from the worst case is the fact that the underlying formal systems are actually compatible, right? So every Lean 3 proof is basically a Lean 4 proof. And obviously, we really hope that we don't have to do this again in Lean 5. I mean, I don't know whether Lean 5 is going to exist or anything like that, but Lean 4 will present its own challenges for porting out of it. So here's some resources, and I'm open for questions.
Thank you very much, Mario. Yes. So actually, there were some questions in the chat. I don't think you had a chance to look at them.
Oh, I will.
Seem to be rather technical, but if you have just quick look at them, maybe yes. You may want to say something about this.
Yes. Let's see. Could you use Olean port as a first approximation and then manually edit the Lean 4 output? Yes. So I would say that all 5 strategies are actually viable. They just require different amounts of user intervention. Olean port only provides binaries, I think, so you don't get Lean 4 source files from that. Oh, this is responding to. How are doc strings surviving porting? So the doc strings attach to a definition. So if you use, slash dash dash before a definition, that's considered a doc string that's attached to the theorem. Those are actually logical content, and they are preserved. Similarly, module doc comments are also actual formal entities. They are preserved in the translation, although there is an issue with that around Lean 4's handling of module doc comments at the moment. However, the plain dash dash comments or slash dash comments, which are just regular comments, you can put them anywhere. They count as white space to Lean 3, and so they are not preserved through the AST port. So this is going to be a concern if anyone uses those kinds of comments heavily. There are ways that we could try to retrieve that information. Oh, in particular, the header of every Lean file is a regular comment you know, the copyright header. So we're probably going to need to at least preserve those. Oliver Nash says, could you use binport to validate that the efforts of some other porting strategy do not lose theorems in the shuffle? Well, so with porting, I think that the concerns around losing theorems is a lot less. I guess you're saying that if we have a mostly manual proof approach, then binport will be able to catch the exceptions. And I think you're right. I think that having any porting tool is really going to make sure that this won't happen, because you're actually trying to keep things in sync in a way that's formally checked. Makarius says, how long will this take? That's a good question. I mean, my guess is like a year. That's sort of I mean, Lean 4 is still evolving. We still don't know what, you know, there's still a lot of like core components of Lean 4 that I think like tactics that don't exist yet. So I would guess that it's going to be around a year before we have Lean 4 and Mathlib in a suitable condition. But it might be less, and it might be more. I mean, it's a time estimation is really hard. How many lines of source level proof have been ported so far, and how many are planned to be ported? Right now, we haven't really started the proof in earnest, and to some extent, we're actually trying to hold people back from doing that too much. So Mathlib 4 has a number of manually ported files, and I'm okay with that for the most part. But there is a concern that the more manually ported files there are, the more they're going to clash with the automatically ported files once the automatic porting is ready. So it's sort of gonna make things more complex as we get to that point. So and then also there's a possibility that, you know, I don't want to ask people to do a bunch of work that we're going to delete later, right? So so far, Mathlib 4 is an experimental repository. It doesn't have that much material. Is there a Lean 4 version of the LST listing language set? Yes. You can talk to me on Zulip about that. I'll send it to you. Kevin Buzzard says, I would like to plug Mathlib 4. One of the things I found most exciting about Lean when I joined in 2017 was that I could make the complex numbers and get my name into Mathlib. Mathlib 4 is an informal manual port. Come and make schemes in Lean 4 and get your name into Mathlib 5. What? Mathlib 4. Oh, that was a mistake. We welcome beginners to come and do so porting. Yeah, so I do agree with Kevin Buzzard here. Do come and join the porting. We are desperately needing a bunch of tactics to fill in for all of the missing tactics in Lean 3. Aurelian has been working on that, but I think that lots of people can join in. There's lots of bigger tactics like Ring and Linarith and CC that need some serious work in order to be implemented in Lean 4. So that will be very.
Mario, it's really easy to make definitions.
Mm-hmm.
Porting definitions is, you don't need that many tactics. Yeah,
that's yeah. Porting definitions is well, okay. Porting definitions is easy. Porting meta tactics is not easy because the definitions are different, right? So you have to make use of different commands. I mean, I would say that it is fairly possible to just look at the old thing and then write the new thing and just follow what it's doing, and it will basically work.
I think I love making schemes in computer systems. So we need. Why don't we just make schemes in Lean 4? It'd be really good fun, just manually. And who cares if it gets overwritten by a computer program in the end? It'd just be a fun project.
Yeah, and I think that by the way, one of the really important things to do about porting right now is you should really take note when you're doing something that you could have done in Lean 3 and there's something that makes it hard to do in Lean 4, because those are things like I'm sure it's possible for you to work around it in the moment, and I know that that's everyone's instinct, but it's really important that we gather data on the ways in which Lean 4 is less pleasant to work with than Lean 3, so that we can fix them, right? We really want to be able to make the ongoing, like even once the port is done, we want to be in a better place than we are now, right? We want Lean 4 to be better in every way than Lean 3. So it's really important for us to find all the places where it isn't so we can fix them. Florin Rabbit says, I imagine that a lot of Mathlib could benefit from refactoring. Are you considering that as well? I would say for the porting effort, this is no, and for very important reasons. I think that it will be very difficult to keep to be able to port in any sane manner, especially a largely automatic method, if we start changing lots of things at the same time. It's sort of going to compound a problem on top of another problem. And I really worry that if we take that route, that we'll just never finish, that we'll just get bogged down with all of the changes and lose hope. Can you adapt these tools to steal already formalized maths in Coq? Yeah, that would be great. I mean, I think that a version of AST port for Coq would be super useful, and you would be able to do exactly the same thing here. I think that there would be a bunch of new challenges that would arise, like things in Coq that don't exist. But to be perfectly honest, I think that we'd be interested in knowing what those things are, so that we can have the best of everything. I don't think anyone would disagree with that. Jeremy says, I really miss our intros and our cases. Yeah, we're working on that. I definitely want to get that one into Mathlib 4 soonish. Will Scheme in Lean 4 be different from Lean 3, Kevin? I'll let Kevin answer that. Isn't intro now as strong as our intro? It's not quite as strong as our intro. There are some things that our intro has a whole little sub language there. Like you can cancel hypotheses, and you can put type descriptions in places where intro wouldn't let you. So intro has been improved in Lean 4. It allows you to do pattern matching and other things, but it's still not quite the same as our intro. Is there a plan for intro to be as strong as our intro eventually? I don't know. I mean, it's possible that Mathlib might be able to override Lean 4 Core's intro in order to make it do the job of our intro and sort of fold everything together. I don't expect that Lean 4 Core is going to implement intro the way we want it for Mathlib. Okay, I've run out of the questions that are on the chat now, but
all right, so are there any questions from so actually I have one, and I would like to ask you about the situation where you are doing extremely well, trying to convince more and more mathematicians to use the system. And so what's the best strategy for that, if we don't count Kevin's special effects? But do you think that formalizing things like the Peter Schultz's result you mentioned, this is the right or the only way to attract mathematicians?
So I do think that is it's, if Kevin's here, he might want to add some more to this, but I do think that so talks definitely help. Talks to the public, not talks to other people who are already in the field, definitely help. There's more general presentations about Lean, more things targeted at new users, trying to make it easier, more accessible. I think that those are all very important. And something else. I think that being able to make it understandable to the layman is really important for being able to increase the usage and usability of the tools. And I think that that's one area where Lean is definitely better than all of the other systems that I've used. It's really focused more on that aspect, and I think it shows.
Okay, thank you. Thank you very much for this very interesting and inspiring, I believe, talk. And so we now move on to one of the